Morning, guys. Thanks for coming. So my name is Jeroen Soeters. I work for a company called ThoughtWorks. I'm Dutch, hence the funny name, as well as the funny accent. I give you guys a little bit of help how to pronounce my name, because everyone is miserably failing at that. So I'm going to talk about Neuro Evolution, which is a branch of AI that uses evolutionary computation to generate neural nets. So let's first take a look at neural nets. So what is a neural net, right? So a neural net can be defined as a model of reasoning based on the human brain. So our brain is this densely interconnected set of neurons, which are effectively just nerve cells. We got about 10 billion of them and 60 trillion interconnections between them. And every one of these nerve cells is like a little information processing unit. Now, the interesting thing about our brain is that it exhibits plasticity. So that means those connections between those neurons, the strength of them can get stronger or weaker. And typically, like connections that lead to the right answer, they get stronger, and connections that lead to the wrong answer, they get weaker or completely disappear. That doesn't always work. If you're late at the conference party and have to decide whether to take another beer or to go back to your hotel room and work on the slides, that might fail, but generally that seems to work. So let's take a look at these neurons, like how they actually do their work, right? So a neuron has a very simple structure. So they have a cell body called the soma, and then they have these arms reaching out of the soma, which we call dendrites. And these arms are there to bring signals into the soma. So electrochemical signals come into the soma and they build up a potential. Now when that potential hits a certain threshold, the neuron becomes what we call activated, and the neuron will propagate that signal via the axon through other neurons, and then these synapses, these other arms that we see there, that's where communication takes place. So synapses of one neuron communicate with dendrites of another neuron. Now, if we were to do this, to simulate this in a computer, right, how would that look like? So first we're going to change the terminology a little bit. As in computer science, we don't speak about dendrites and synapses, but we talk about input signals, weights, and output signals. Now, this model was proposed in 1943 by Warren McCulloch and Walter Pitts, and it's still the basis for all artificial neural networks these days. So how does this work? So basically, this neuron here calculates its output by taking the weighted sum of its input. So basically, it does a dot product there of x1 times w1 plus x2 times w2, adds those all up in a neuron. It compares that with some threshold value. If it's higher than the threshold value, the output will be 1, so the neuron is activated. Otherwise, it's -1. So in other words, we just apply a sine function there. That sine function is what we call an activation function, and that by no means needs to be a sine function. We're going to see an example where I actually use the step function. In deep learning, popular functions are like a sigmoid or a hyperbolic tangent. You can use anything, almost anything for that. So now we know like how this neuron calculates its output, but we don't know like how it learns, right? So in 1958, this gentleman, Frank Rosenblatt, came up with an algorithm to train one of these neurons. And the algorithm is called the Perceptron learning rule. And it works as follows. So we start with a training set where we have a set of inputs for the neuron and expected outputs for that input. And we're going to show the neuron those inputs. And for every example P, we're going to calculate the output. Now here we know the desired output, which is YD, and we know the actual output, which is YP, and we're going to first calculate the error, right? So it's the desired minus the actual output. And what we're going to do then is we're going to change these weights. So in this case, if the error is positive, so that means the desired output is higher than the actual output, so we need to increase the weights a little bit. Otherwise, we need to decrease the weights, and that's what this rule is doing, right? So we add some constant factor alpha times the current weight times the error to the current weight. This looks something like this. So we set these random values and the threshold. We set the weights and the threshold to some random values. Then we activate the perceptron. Basically, we show it an input, and we see what the output is. And then we're going to up those weights until those weights converge. So let's see a little bit of example. I think most of you guys know the OR gate or the logic gates, right? So here I have the truth table for an AND, OR, and an XOR. We're going to try to train a neuron to function as an AND function or an AND gate. So here I have this in a tabular form. So we're first going to pick some random values. So we set a threshold to 0.2, We set that learning rate alpha at 2.1. That's not random, by the way. And we set our initial weights to some random values. And now we're going to calculate the output, right? So we have to do the dot product. So that's 0 times 0.3 is 0, plus 0 times minus 0.1 is 0. Threshold is 0.2, so it's less than the threshold. So the actual output is 0. But for 0 and 0, we expect 0. So the error is also 0. So we don't do anything with the weights. Next one. So 0 times 0.3. So this is minus 0.1. Also less than 0.2. Actual output again 0. Desired output is 0. So the error is 0. Again, we don't do anything. Now the next one. So now we have 0.3 plus 0. So now the actual output is 1, right? Because 0.3 is higher than the threshold. But the inputs are 1 and 0, right? And for the AND function, 1 and 0 should give us a 1, or should give us a 0, right? So we have an error now. So the error is minus 1, so this means we update the weights. And this basically we keep on doing. Every time we show a complete training set, we call it an epoch, and I'm going to just walk through a couple of these epochs now. So it's 2, 3, see sometimes the weights change, sometimes they don't. And now we see in the 5th epoch that everywhere our error is 0. So this means now for every set of inputs, our neuron is actually giving the correct output, right? So we have trained this neuron now how to act as an AND gate. Now, what we are actually doing here, basically this neuron is what we call a binary classifier. So you can only solve a limited number of problems with this, and you can only solve problems that are linearly separable. So that means the the output space needs to be, you need to be able to divide that by a line. And you see, if we highlight points where the output is 1 as black and the output is 0 as these open dots, you see for the AND and OR we can cross a line to separate that output space. But for XOR that's not possible. So it took people quite a while to figure out how to solve this problem. And turns out, if you connect a bunch of these neurons in what we nowadays know as a neural network, then you can actually solve arbitrary complex problems. If you have one of these hidden layers, so basically there's a few layers. First layer doesn't really do anything. It just takes the inputs and forwards that to every neuron in the next layer. And so on and so forth. It's a fully connected network. And turns out with one of these hidden layers you can represent any continuous function, and with more hidden layers you can also represent non-continuous functions. So they also call this escalating to higher dimensions. So if you can't separate with a line, you try it with a plane or higher dimensional structures. Training this works much same like the perceptron or the neuron we saw before, as in you show it some inputs, you calculate the output, and then you go back and you update the weights until you have found a configuration that gives you the right output for any given set of inputs. And then you hope that that also works if you show it examples that are not in a training set. Right? So this algorithm is called backpropagation. It's a very compute-intensive algorithm that actually dates back to the 60s, I think. And it's still the algorithm used to train neural nets these days. But there's some limitations to this backpropagation algorithm. First, you need a training set of sufficient size and sufficient variation. Right? If you look Google and Facebook, they actually augment the images a little bit, change the color, rotate a little bit, and show it again to the network to train it to recognize your face. You need to know that topology in advance, so the number of hidden layers and the neurons per layer. They also call that hyperparameter tuning and in deep learning. No recurrent connections are allowed, so you cannot connect from a layer n to any neuron in layer n of it's smaller than n. And the activation function that we saw before, it needs to be differentiable because that's how the backpropagation algorithm works, right? It uses it differentiates the activation function and tries to minimize the error rate. It really only works well for supervised learning problems, right? When you have that training set available. And even then nowadays you could question, right? We saw yesterday in Fred's talk a turtle disguised as a gun, I think. And a couple of weeks ago there was a paper came out, the 1 pixel attack. Anyways. So it's roughly 200 years ago, I think, that young Charles Darwin went out on this HMS Beagle, initially actually to find evidence for the theory of creation that was laid out in like Genesis, right, the first book of the Old Testament. But as he was on this journey, as we all know, and he was gathering more and more data in like true like lean startup style, he pivoted slightly, and that's what ultimately led to like what the classical theory of evolution, right? And this theory of evolution, together with Weismann's natural selection and Mendel's genetics, is what we now know as Neo-Darwinism. Neo-Darwinism is based on processes of reproduction, mutation, selection, and competition. Now, in the early 70s, there was a gentleman, Mr. John Holland, that was wondering if he could emulate that process in a computer. So what John did was the following. He described a solution to a problem that he wanted to solve as a series of bits, a bit string of zeros and ones. And then he came up with an algorithm to move from one population of these chromosomes, as he called them, to the next generation of these chromosomes. He did that by defining a fitness function that would tell him what is the health of one of these chromosomes, how well does that perform. And then he had genetics-inspired operations, crossover and mutation, to like select parents from a population, cross them over, and then with a very small chance do some mutation on them and put them in a new population. So crossover would look something like that. He would, based on like the fitness score, he would take two parents, he would cut them in half and like join the halves. And mutation, if he had that child with a very, very small chance, very now and then would like make a small modification, just like nature does it as well. So let's look at a more real life example to make this a bit more concrete. So for doing one of these algorithms, we need to walk to sort of a checklist. Right? So we're going to do that for, one time in schematic form. Basically what we're going to do is this. We're going to generate a population. Right? We're going to calculate for every candidate in that population, we're going to calculate the fitness. And then until some termination criteria is satisfied, we're going to do the following, right? We're going to select a pair for mating based on fitness. Based on like a crossover and mutation probability, we're going to cross them over and we're going to do a slight mutation on the child. Then parents and child go into the new population, and we keep on doing that until we have a new population of the same size as the original population. And we keep on doing that until some termination criteria. And that's typically either you run it for n number of generations or you have some target fitness in mind that you want to achieve. So, traveling salesman problem. So, classical computer science problem, right? Given the salesman, a list of cities, and the distance between each pair of cities. Now, what's the shortest route this gentleman can take to visit all the cities and return to the origin city? So this is what we typically call a NP-hard problem, right? If you add cities, this typically, like brute force, is not an option because it's very soon taking years or more to solve this problem. So let's use the genetic algorithm, right? So first we're going to represent the candidate solution as a chromosome. Well, it's pretty easy here, right? We can just list our cities in our chromosome, like a list of characters, and we're done. So the genetic operators, these are a bit more tricky because remember John was cutting those two in half. Like that doesn't really fly here, right? Because we might end up with duplicate cities or we might miss cities. So we need to be a little bit more creative here to solve that problem. So what we do is following. We cut some part of the original parent. We place that in the offspring at that part. And then we start taking from the second parent. And every time we see a city that we already have, we just skip that, right? So we take B, we take E, A we already have, so we skip, so we take F, and so on and so forth. So that's crossover. A mutation is, again, pretty simple. Right? We can do the same thing like John did. We pick two random genes and swap them around. And then we need to have a fitness function. Well, fitness function is also easy, right? Because we know here what's the distance here, right? So it's basically the distance between C and B, between B and G, until the distance F to C, right? So we can just add all these distances. And if we want a fitness higher for like a shorter distance, we can do 1 over the total distance, and that will be our fitness. And now we need to only choose our initial population size, crossover and mutation probability. It's not really, as far as I know, like hard science to get to these numbers. Typically, numbers that work well are like a 0.7 crossover probability and a very small, like 0.0 or 0.005 even for the mutation probability. So now I'm going to show how that actually looks like. So what we'll see here, so we have 250 cities now. And what we'll see here on the screen is the solutions that the algorithm is generating, right? So this is every time the best solution we find in every generation. And we see here that very soon this algorithm converges to pretty decent solution, right? Yeah, there's some optimizations right here. There's still like a weird loop and top left corner, and it will improve that over time. And not all of this, and I have it running for 1,000 generations now. But really the key takeaway is here that the genetic algorithm will give you a solution that is good enough in a very, very like reasonable amount of time, right? Where you'll be calculating for many months, or I don't know even how long, you'd be calculating with 250 cities, right? So it's quite like a nice solution. So it does not guarantee you the optimal solution, right? So here we still see that's not optimal, right? But it's good enough for most cases. So this works well for vehicle routing, resource allocation, scheduling problems, all these type of problems. Okay. Now we've seen neural nets and we've seen evolutionary computation. Now let's see how we can combine those two, right? And this technique is called Neuro Evolution. So research to Neuro Evolution has been happening since the early 90s, but some like groundbreaking work has been done in, started 2011, 2012, I guess, by this gentleman, Gene Schur, who created DXNN, which stands for Deus Ex Neural Network. And DXNN is a TWEANN, which stands for Topology and Weight Evolving Artificial Neural Network. And basically, DXNN is it's a general purpose platform to generate neural nets. So that means like the platform to generate these networks is decoupled from the actual simulations that you use to train these networks in, right? So you can use it for many purposes. So let's take a quick look, like what does it mean if we want to plug in a simulation to DXNN, but what all do we need? Right. So we need three things. We need some sensors, and sensors, they provide input from the simulation or the environment to the neural network. We need some actuators. Actuators say they take the output of the network and they make some change in the environment. And then again, we need to define a fitness function to basically score a run of a neural network in that environment. So give some more concrete examples, right? Say Roomba, right? I've got one of these in my living room. So the sensors on this Roomba are, it has like a bumper sensor, there's like a bunch of IR sensors on the side and on the bottom, and it has a battery sensor, right? Actuator as well, it just has motors, right? Like servos or whatnot to like drive that guy around. And a fitness function, you could do something like percentage of the environment cleaned plus the time it's active minus the number of furniture bumps or whatever, something like that, right? So another example, so Forex trading, right? So foreign exchange or currency trading. So you could say the sensors are the market data, right? So for the different currencies, like the current price. The actuators is like buy, sell, or hold, right? And the fitness function is, well, the number of correct predictions minus the number of incorrect predictions. And you can use that for many more things, right? You could use data compression, NPCs, all kind of stuff. So now let's go back to our genetic algorithm, right? Because what does it mean to like generate that network using evolutionary computation? So we go back to our checklist. So first, again, we need to represent the candidate solution as a chromosome. Now you can imagine this fixed length bit string is not going to work anymore, right? Because there can be arbitrary amount of information in what we call the genotype of a neural network. And so it's very simple, actually, the chromosome here. It's basically a data structure that contains all the information of the structure of that network, right? So we'll see in a bit, this is written in Erlang. So it's just like a massive like list of nested Erlang records that contain like which sensors we have, which neurons we have per neuron, like the inputs and the weights and the activation function we use, which actuators we have, and so on and so forth. So now we need to define the genetic operators. Well, now if you think about that crossover operator, right, like having these two and like crossing them over, if like a little bit of intuition will tell you that won't work if you have two like massive neural networks of millions and millions of neurons. If you just pick two random branches and swap them around, like chances of that ending up with a better performing neural network, that's close to zero, right? So that's not really going to work. So we're going to park that thought a little bit, and we're going to come back with that to this later. Mutation is, again, it's very easy. There's actually a whole bunch of mutations that we can do to a neural network. We can mutate the activation function, right? That doesn't need to be differentiable anymore. We can have like every neuron has a different activation function. So we can change that one. We can add connections. We can add neurons. We can something called outsplicing. So kind of removing a line and adding like a neuron in between. And like tons and tons more, right? You can imagine like how these things would look like. Important thing to note here that these things I just showed, they're like complexifying operators. Most of these have an inverse, which are simplifying operators. Because the algorithm that we'll see in a bit, it will prefer smaller networks over larger networks to prevent network bloat, right? So it will like optimize for pruning as well. Now we need to define the fitness function. Well, that we've already seen, right? Because the fitness function is just the performance of a network in a specific solution. So it really depends, right? The fitness function for that robot was different for the fitness function of the Forex trading agent. Okay, and now we get to this. We need the population size, crossover probability, and mutation probability, right? So now we need to do something with that crossover, right? We need to solve that. The way DXNN solves that is it basically doesn't do crossover, and it combines those two in one. So instead of doing crossover, it does this thing called random intensity mutation. So instead of picking two parents, it really picks one parent based on like a fitness score again. What it does then, it clones that parent, and then it applies a random number between 1 and the square root of the network size of mutations to that agent, right? And so what this gives us is that it allows for like very small improvements, right? If we have already a well-performing network to like improve on that. But it also allows for pretty large mutations, right? To jump out of local optima. Yeah, so the reason why DXNN works so well as it does is because of the core algorithm, and the core algorithm is what we call a mimetic algorithm. And a mimetic algorithm is an algorithm that works on 2 time scales. So what DXNN does, it separates the what calls the global search, which is basically searching for the topology of the network, from the local search, which is searching for the optimal weights for each of these networks. So for the global search, it still uses like a population-based algorithm, like we saw with genetic evolutionary computation. But for the local search, it uses stochastic operators, and we're going to see what that means. So first, we'll look at the topology search here. So what we do is we generate a population, right, of completely random networks. So these start off very small with just one neuron and maybe a different activation function. And then we're going to apply these to a problem. And what that means is we're going to apply this network in a simulation, and we're going to see what is the best fitness we can achieve in a reasonable amount of time with this configuration, right, with this topology. We keep on doing that, and I'll explain that algorithm in a bit, until all these networks are done. And then what we do is we calculate the effective fitness. So those networks report back to fitness, or the simulations report back to fitness. We like take into account this network size. First thing we're going to do is we're going to just drop the bottom 50% of that population immediately. And then of the top 50%, we're going to do what's called mutant allotment. And that means like every agent there gets assigned a number, which is the number of clones it's going to produce. So that means if something has a very high fitness compared to the rest, in that the rest of the population, it'll get more offspring. If it has a very low fitness, it can still drop out of the population there. Now, then we do this offspring creation, we do the random intensity mutation on the topology, and we start again. Now, this local optimization is very easy, actually, what happens here. Basically, we're going to apply the network to a problem, and we see, okay, the fitness that we have here, is this better than the best fitness so far? If this is the case, we back up those weights because that's apparently a configuration that we want to keep. We change the weights again, like this is also random intensity mutation now for the weights, and we're going to try that again, right? If it's not better, then we go back to our previously best weights, and we keep on doing that until some stopping condition is reached. And stopping condition is if we didn't improve, say 50 iterations in a row, then we just stop and we report the best fitness so far. Working on that last night late. So Erlang, right? So I guess most people here are familiar with Erlang, so I don't need to explain much. So for everyone who's only running Idris in production and doesn't like touch Erlang at all, Erlang is a concurrency-oriented programming language, right? Built around the actor model, so you have like many like small processes that send messages to each other in a VM, right? And if you read Joe's thesis, he emphasizes on this concept of having an isomorphism between the problem and the program, and having this one-to-one mapping kind of your problem to the program in a concurrency-oriented programming language, which makes it much easier to reason about your program. And that's exactly what we get with DXNN, because that genotype, as we saw, we can map that literally one-to-one onto Erlang processes, right? So every one of these neurons, these sensors, and these actuators, they'll just become an Erlang process, and they start sending messages to each other. Now, this message sending, that's kind of the core in Erlang, right? So what I want to do is I want to explain you guys the architecture of DXNN, doing that by showing you the messages that flow back and forth in the system. And we're going to start by zooming all the way into the deepest level of DXNN, and that's the level of one of those neural nets. So most of you should look familiar by now, right? So we have sensors, we have actuators, we have neurons, the scape, that's really the simulation. And then we have an element cortex, and the cortex is really only there to synchronize between the network and the simulation, because it needs to know like when actually to get the input and when to process the output, right? So what happens is this. So the cortex sends a message sync to the sensor, and the sensor then sends a message sense asking for data to the scape. The scape sends back percept, and percept also contains the input vector. And then, like in every neural network, right, the sensor will just forward that stuff to the next layer, and ultimately that will all aggregate in the actuator. And the actuator will send then an action to the scape. Upon which the scape does something, right? It buys a currency, or it like moves the robot, and then it returns back a fitness that we have so far and a halt flag. So basically, are we done, right? Do we not have any more historic market data? Did the robot run out of battery or fall off the stairs? And the actuator sends back a sync signal to the cortex. Now we're going to zoom out one level, and now we're going to see one extra element, and that's called the exoself. And what the exoself here is doing, the exoself is the component that's responsible for this local search, right? The stochastic hill climbing algorithm. So that's what the one's going to see what's the best fitness this one can achieve in a reasonable amount of time. So the exoself sends, or gets actually from the cortex, okay, I'm done, like this is my fitness, and the exoself will then say, okay, is this better than our best fitness so far? Yes, it is. So we're going to back up these weights, right? So we send them a message to all these neurons to back up their weights. And now this random intensity mutation happens. And to some random neurons, we say, OK, change your weights, please. And then it says to the cortex, reactivate. And basically, we drop back into the previous loop, right, on the previous screen. And now we're going to zoom one more level out, and now we're really on the highest level of DXNN, right? So here we have the population monitor, and here we'll see this global search, right? Looking for the best topology of this network. So what happens is population monitor spawns a random population of networks, all with like different topologies, and it's going to say then like, okay, guys, go for it. Please let me know what's best fitness you guys can get. So at this point, all these little exoselves keep on starting to crunch, right? And going to see, okay, what's the best fitness we can achieve here? And once they're done, like one by one, they'll send back to the population monitor, okay, I'm done, and they'll report back their fitness. What happens then is population monitor drops the bottom 50% of the population, clones to, and here does random intensity mutation, and it was too late last night to get that animation going, so you just have to imagine that these now change topology over there. And then it basically starts all those guys again. So that looks all very easy, but unfortunately it's not. So there's a lot of like little details to actually make this work and that you need to think about. Right, so I'm going to go over a few. I don't know how much time we have. 10 minutes, okay, cool. So recurrent connections. So here we don't have this limitation of like connecting back to a layer, a previous layer, right? Because we're not doing backpropagation. But you need to think very carefully, right? So for those of you who took a hardware class, right, which element has a recurrent connection in the circuit, right? That's the flip-flop, right, or a latch. And what does a flip-flop do? Well, it creates memory. Right? And that's exactly the same thing that also happens in the neural network. When you make a recurrent connection, you create memory. So that means if you're like training a neural network to solve the XOR problem, well, you better make sure that you show the examples in random order every time, because if you show it in the same order, the network might start understanding in what order you're showing that, and then if you show an example outside of training set, it doesn't know what to do with that. So the next one is kind of, you know, when you learn how to bike, that doesn't affect like your ability to walk, right? You might like damage some sensors or actuators along the way, but like the part of your brain that's responsible for walking, that doesn't change, right? And this is the same with here, right? If you add elements to the network, you want them to work well together with your already like well-performing network, and you don't want to change like things randomly all over the place. So that's really what that thing does, right? So every element gets added to the network gets a generation number, and elements with a higher generation number have a higher chance on getting mutated. Neural plasticity, basically these neurons can evolve things like Oya's rule or Hebbian learning, public state, steady state evolution. So that's actually an interesting one, because what we saw is just like one network and one simulation. But you can actually have multiple of these networks working in a simulation, and you can do sort of A-life simulations, right? So you have a population of predators and prey, and they're like battling against each other, and then you don't have that. You create a new population, right? But you keep the population in there at some stable number once like candidates drop out of the population. So last, I want to look at a little quick benchmark. So this is a typical benchmark for neural nets. So the idea is following, right? So it's called pole balancing benchmark. So we have a little track, and we have a card on that track. And on that card is a pole, and that pole is connected with a hinge, so it can tip over. Now, the idea is the network gets as input, and there's different variations to this one. It gets like the position of the card on the track, the velocity of the track, velocity of the card, the angle of the pole, and the velocity of the pole. And it needs to produce a force, either positive or negative, such to keep the pole balanced. Right? That's the benchmark we're running here. So here I just recorded this in my Erlang shell, just to show you guys that it actually also works. So here I'm just starting up the XNN platform. And I'm starting the benchmark now. And you should see, like it should look pretty familiar what we're going to see now. Right, so you'll see, you see these agents reporting, right? And the population monitor will tell, okay, this is how much agents I have left, right? 6 left, 5 left, 4 left. And then every, like, when it has all the 10, it like, you see this like blob when it like generates a new population, basically, right? And these agents, they report back their fitness, evaluations, basically like how many like variations did I try before I got to this fitness. Yeah, and this just keeps on going, I think. I'm not gonna wait until this thing completes, but I'm just gonna show you the benchmarks results. So I have to like do a little bit of explanation here, because we see some of these benchmarks, they have this little star. And this little star means they're actually not TWEANNs, so they don't evolve topology and weights. They have a fixed topology, they only evolve the weights. So it's not really like fair to compare with those guys, as they're cheating a little bit. So you really have to compare with need. And as we see here, like we're more than 3 times as fast as neat, right? And the second version is almost 4 times as fast as neat. So this second version actually is the one you built in this book. So if you wonder, like, how do I know all this stuff? Well, I wanted to learn some Erlang a couple of years ago, and I wanted to build something non-trivial in Erlang, and that seems pretty non-trivial to me. So I found this book. Yeah, and in this book, you really like are developing the second version of DXNN. So you're really building a state-of-the-art neuroevolutionary platform throughout this book. It's a really great book. It's full of like great ideas. I would recommend if you're going to go through it, like write the code and start introducing some kind of engineering practices from the start, as the code is like, it has like 0 tests and there's like gaps between the chapters, so there's pieces of code missing that you're gonna need to fill in yourself. So if you don't like rewrite it and start like typing the examples, like you go absolutely mad. Yeah, that's all I had for you guys. So happy to take some questions.
Is this a proprietary effort, or do you release anything open source or something?
No, so for me it was just like a learning effort to just figure out how this stuff works. The original stuff is open source. My implementation is also on my GitHub. Yeah, it's really like learning, not really using this for any practical things.
Anyone else?
By the way, the guy himself, like he is using this. So this works particularly well in like robotics, right, where you don't have that training set, and also it's maybe less useful, but you know you have these programs like learning how to play Atari games. Like it works like very well for those things as well, as the network learns what information is important and what action to take. But the guy himself, unfortunately, like he's not in academia anymore. So DXNN2 is the latest version that's open source. DXNN3 is all proprietary, and he's like using this stuff for training unmanned aerial vehicles right now. But unfortunately, that's all like proprietary.
Any other questions? I guess I've got one actually.
Yeah.
So I mean, Erlang floating point computations. Did you write this stuff in pure Erlang or drop down to Nib?
So it's all pure Erlang because actually, if you think about like neural nets and you take away backpropagation, all that's left is really message passing, right? So every one of these neurons in a layer, all it needs to do is it needs to wait for the neurons in the upstream layer, right? So it just has a list of bits that it expects a message from. And then when it has like the information, it applies an activation function and forwards it to the next layer. That's why Erlang is such a like nice, very elegant solution to this problem. And you don't really need, if you do backpropagation, then it becomes very compute intensive, and that's why people are running that on GPUs and stuff like this. But for this, it's really all message passing.
Even for message passing, perhaps memory sharing might be a faster solution?
If the messages are very large, I guess, yeah. And maybe we can rewrite it in Pony, but...
All right.
You got any more questions?
Cool. Thank you so much.
Thank you.